In our final unit, our final relatively short unit, we're going to go deeper into physics. We're going to look at what happens, for the most part, inside the atom. Now, we're going to start off by what happens around the nucleus. We know now that the atom consists of a nucleus, a positively charged nucleus, and that there's electrons orbiting around that nucleus. We're going to start off by looking at what happens outside the nucleus, the electrons that orbit around the nucleus. And then we're going to go a little bit deeper and talk about the nucleus itself and some of the processes that take place inside that nucleus. Let's go back a little bit, though. Okay, prior to 1897, J.J. Thomson, we didn't even know there was anything that existed inside the atom. There was no subatomic physics. There was no atomic physics. The atom was the atom. The atom was as small as it gets. J.J. Thomson comes around, though, in 1897, and for the first time discovers that there is something smaller than the atom. There is these electrons floating around inside this atom. In fact, his conclusion, after he did an experiment, which we'll tell you about in just a second, was that the atom consists of not just negative charge, but positive charge as well, a sea of positive charge. Like we talk about chocolate chip cookie dough. The dough would be the positive charge. Floating around in that positive charge would be a whole bunch of little chocolate chips or a whole bunch of little electrons floating around. Again, we know that's not true now. We know that's not the case. But it was a huge step forward in the sense that it's the first time that we've shown that there's actually something smaller than the atom. Now, how did he come up with that conclusion? How did he draw that conclusion? Well, he used a device called a cathode ray tube. A cathode ray tube, he didn't invent it, by the way. A cathode ray tube had been around for probably 40 years or so prior to Thomson. Lots of people had used cathode ray tubes in various experiments, whatever. Lots of people had made observations with the cathode ray tube. But it wasn't until Thomson in 1897 that we actually discovered something important with the cathode ray tubes. So what is a cathode ray tube? Well, this is one of the older style TVs. The older style TVs that you see in the corner of the room right now. Okay? The older style TVs that you might have in your bedroom or your basement. Okay? You can't buy them anymore. So if you've got a newer TV, it's not going to be a cathode ray tube. It's going to be an LCD or an LED or a plasma TV or something like that. But everybody's seen these older style TVs. Inside these older style TVs is this glass tube that's evacuated. In other words, all the air is sucked out of this glass tube. If you've ever had the back off of one of those TVs, okay, you can see literally this big glass tube. Okay, the front of it being the screen of the TV. That's why the TV is so heavy. Right? You try lifting one of those things, they weigh a ton because they're made out of glass for the most part, thick glass with a few components inside it. Actually, let me draw a picture here before I show you the one that I have already drawn. The glass tube, a bit of an exaggeration, but the glass tube looks something like this. Okay, this would be the screen here. In fact, this screen, by the way, is painted with this phosphorescent coating, we say. That will cause the screen to glow when it gets hit by a charged particle. So in the end, that's why we see the image that we see. A bunch of electrons hit the screen, cause the screen to glow. That's the picture that we see, is the glowing screen caused by this phosphorescent paint glowing. Well, inside this glass tube, we've got a couple of electrodes. Hooked up to a power supply like this. A little bit more complicated than this because this power supply is kind of inferring that it's a few volts, right? You have to have thousands of volts inside your TV. There's a transformer that changes the 120 volts coming out of the wall to thousands of volts to allow the electrons to jump across that gap. That's why you shouldn't try to service one of those TVs yourself. You shouldn't try to take off the cover and try to work on it yourself because there's several thousand volts that you could electrocute yourself with. Okay? We'll simplify the diagram a little bit, though, and just show a direct current power supply with a negative side right here and a positive side right here. That gives us a negative electrode right here and a positive electrode over here. Well, prior to 1897, lots of people had done this. Lots of people had used this cathode ray tube. Lots of people had observed this mysterious greenish glow that left this electrode, the left electrode, and went towards the right electrode. Now, there's a little bit of a hole in the right electrode, so they keep going. This greenish glow, this mysterious whatever, goes toward the screen, causes the screen to glow. Nobody knew what this was. Lots of theories. Some people said it was light, some kind of electromagnetic radiation. Some people said they were charged particles. Okay? Lots of people had ideas as to what they were, but nobody really knew what they were until Thomson. By the way, nobody knew what they were, but people called them cathode rays. Hence the term cathode ray tube. These are called cathode rays. Nobody knew what they were, but they knew there was some kind of mysterious ray coming from the, oh, this is going to confuse you if you took chemistry, coming from the cathode and going towards the anode. Why is that going to confuse you if you took chemistry? Because it seems to be reversed, right? Okay. Which way do the electrons go in chemistry? I'm sorry? Anode to cathode? Anode to cathode, right? Here they're going from cathode to, well, not really, right? They're going around here from anode to, it's a matter of perspective, right? It's just a matter of perspective. So we're going to call this the cathode. We're going to call this the anode. The electrons from this perspective are going from the cathode towards the anode. We call it the cathode ray tube. Keep in mind, though, as we're doing this, we didn't really know that these were electrons. We knew there was something going from the cathode to the anode. Okay, we call them cathode ray tubes. All right. Thomson couldn't do anything other than what everybody else had already done with this stuff with the cathode ray tube as it exists right there. So what does he do? He's a smart guy. He introduces a magnetic field over here. Brilliant, he says. I'm so smart, he says. You got a magnetic field over there. What happens? Well, you got a magnetic field over there, and all of a sudden, these cathode rays, these mysterious beams of whatever, change direction. When they enter that magnetic field, they go down like this, right? We know that negatively charged particles will go thumb, fingers, palm points downward, okay? That told Thomson that these mysterious rays that nobody could figure out for sure what they were negatively charged particles. Now, some people might be thinking, wait a sec, negatively charged particles. How do we know about hand rules and negatively charged particles in magnetic fields when we hadn't even discovered electrons yet? Well, we knew about negative and positive. Okay, that wasn't new. We knew that there was negative charge and positive charge. We just didn't know where it came from. We knew about electricity, right? Electricity had been around for almost a century. In 1819, Hans Christian Ørsted discovered the relationship between electricity and magnetism, right? Long before, we're talking 80 years before Thomson ever discovered the electron. We knew very well about the relationships between electricity and magnetism. We knew that if these mysterious rays were deflected downwards in this magnetic field, then these mysterious rays weren't quite so mysterious. We knew that they must be negatively charged particles. Now, didn't tell us anything about the nature of those negatively charged particles, subatomic, but at least we knew they were negative. Thompson says, you know what? I want to know more. I want to know more. I don't want to just know that they're negatively charged particles. I want to know more about these negatively charged particles. So he does a little bit of an analysis that we've done before. He says in this section over here, we'll call it the main chamber. In the main chamber, the centripetal force will be equal to the magnetic force because these particles are going in a circle, centripetal force, and it's caused by magnetism. So centripetal force equals the magnetic force. mv squared over r is equal to qvb. We're going to cancel out one of the v's here. We're left with mv over r equals q times b. All right, perfect, perfect. So then he starts trying to plug some numbers in, but he runs into some problems. He doesn't know what mass is. What's the mass of these particles? No idea. What's the speed of these particles? No idea. What's the radius of the path? Well, he can look at where they hit the screen, because the screen glows where they hit, right? And he can determine from that the radius. So, all right, he's got the radius. 1 for 3. Great. Charge? No idea. Magnetic field? Well, He was the one that put the magnetic field in there, so presumably he's able to determine what the magnetic field was. So we're 2 for 5. We're not very successful here so far. We know that these are negatively charged particles, but we don't know much about these negatively charged particles because of the equation, from the equation that we have with 5 variables in it, we don't know 3 of them. But he doesn't quit. He introduces in between these 2 sections that we already have drawn up here, another section with another magnetic field. But this time he also introduces an electric field. So now he's got one section with just a magnetic field. He's got one section with a magnetic field and an electric field. The electric field, by the way, would have a positive plate on the top and a negative plate on the bottom. Okay, it'd be attached to a battery somewhere or some kind of power supply somewhere. What's going to happen as a result of that? Well, he noticed that if he adjusted these things just right, that he could cause these mysterious negatively charged particles to go straight through. Sometimes these particles, if the magnetic force was bigger, if the magnetic force acting downwards was bigger than the electric force, then they'd be deflected downwards. But if the electric force was bigger than the magnetic force, they'd be deflected upwards. But if the electric force was equal to the magnetic force, then what would happen to these negative particles? They go straight through. The values of these forces, the magnetic force is determined by the speed of the particles. So we adjust the value of the magnetic force by adjusting the speed of the particles. For some of these particles that are going through there, at just the right speed, the ones that are going through at just the right speed, the magnetic force will be equal to the electric force. Now, that's not the case for all these particles. Some of the particles, the magnetic force will be bigger. The particles are going to curve down here and hit the side of this cathode ray tube. For some of the particles, the electric force will be bigger. Okay? They'll curve upwards, and they'll hit the side of the cathode ray tube up here. But for some of these particles, the ones that are going just the right speed, these 2 forces will balance. QVB will be equal to Q times E. Not for all of them, but for some of them. The ones that go straight through. And really, the ones that go straight through are the ones that we care about because they're the ones that enter this main chamber over here and go in the circle. Right? Those are the only ones we care about. Who cares about the ones that are deflected upwards and downwards? They hit the side of the cathode ray tube. Let's look at the ones that go straight through and into this 3rd section here, this main chamber. Q's, by the way, cancel. So it doesn't actually matter what the charge is here, okay, because the charge cancels. If we arrange this equation, we end up getting V is equal to E over B. I don't know if it's quite a eureka moment here, but Thompson recognizes that, look, he knows the value of the electric field. He put it there, right? He knows the value of the electric field. He knows the value of the magnetic field. He can calculate the value of the speed, not for all the particles, but for the ones that go straight through. So let's take that speed that he just calculates, put it over here. All of a sudden, he's just tipped the scales a little bit, right? We had 5 variables. We knew 2 of them. Now we have 5 variables, and we know 3 of them. Okay, it's still not great. We'd still like to know 4 of them so that we could calculate the 5th, right? But 3 out of 5 is a lot better than 2 out of 5. Well, that's pretty much where it ended for him. He couldn't figure out the value of M or Q, ever. He couldn't ever figure out the value of M over Q. But what he did do is say, look, I can't figure out what charge is, I can't figure out what mass is, but at least I can figure out something. I can figure out the ratio between the 2. Now, why is that even useful? Well, let's say somebody comes into this room right now, asks Matt, how old are you? Matt doesn't want to tell. So Matt doesn't tell. Guy doesn't know how old Matt is. Okay. Then the person says, Mr. Dickie, how old are you? I'm not telling you. I'm too old. I'm not going to tell you. So the person doesn't know how old Matt is, doesn't know how old I am. The person doesn't know anything about our ages. But then Matt and I get together and say, you know what? We don't really want to tell them how old we are, but let's give them the ratio of our ages. Okay, the ratio of our ages is 2 to 1. Okay, I'm twice as old as Matt is. Okay? That's not as good as knowing how old Matt is. It's not as good as knowing how old I am. But it's better than nothing, right? It's more information than the guy had when he walked in the room, the ratio of our ages. So Thompson can't find Q, he can't find M. He'd like to, but he can't. So what he does is finds the ratio of the two. Not as good as finding Q over M, Q or M, but it's better than nothing. So let's take this equation now and find the ratio of Q to M. How do we find the ratio of my age to your age, by the way, Matt? Divide it. Divide my age by your age. How do you find the ratio of Q to M? Divide them. So let's say Q over M, the M goes down by dividing, is equal to V over B times R. The B goes down by dividing to the other side. Here's the ratio of Q to M. I can't remember for sure what that number is. I'd have to double check it, but I'm thinking 1.76 times 10 to the 11. Don't write that number down because I'm not positive about it. Bottom line is, it's a big number. It's a really big number. Okay, a giant number. In fact, bigger than any other charge to mass ratio for any other particle ever observed. What does that tell? Well, if you've got a bigger charge to mass ratio than the charge to mass ratio of any atom ever observed, then what do we know about this, Paige? If the charge to mass ratio is very, very big, then the mass has to be very, very small. In fact, smaller than the mass of any atom. Well, if you've got a mass that's smaller than the mass of any atom, then what do you got? Something smaller than an atom. Something that's inside the atom. Does that make sense? So we know that we have negatively charged particles simply by looking at how these cathode rays, these mysterious rays, bend in a magnetic field. But that doesn't tell us anything about the subatomic nature of them. The idea that the charge to mass ratio is so big, therefore the mass must be so small, smaller than any other mass ever observed for particles, that's what tells us it's subatomic particles. That's what led to the discovery of the electron. The idea that the mass is smaller than the mass of an atom. Does that make sense? So what did Thompson do with that? It goes back to our picture here that we drew a few minutes ago of his plum pudding model of the atom, right? Oh, wow, we got these little negatively charged particles. Let's call them electrons. Well, what are they doing? I don't know. Swimming around inside this sea of positive charge. Well, it's not great, but it's much, much, much better than what we had, right? Much better than what we had, which said basically the atom consists of a solid sphere, like a marble. Okay, at least we now know that there's something smaller. The little Whovians are swimming around in Whoville. Something smaller, and we know something about them as well. These little things that are swimming around are negatively charged. Okay, over the next 30 to 40 years, we learned a lot more about what exists inside the atom, but this is really the first big step in the development of the atom, the model of the atom that we have now. Does that make sense? Okay. So what are we going to be asked to do in terms of an analysis? Okay. Clearly, there's some qualitative implications of this, right? The idea of the discovery of the electron. That's pretty big. If our unit is on atomic physics, the discovery of the electron is pretty big. We have to know where that came from, how that discovery developed, right? The idea of introducing the magnetic field and the electric field and so on. But we also have to be able to do the mathematical analysis. There are essentially three sections in this cathode ray tube, two sections that we've looked at already. The third section that, I call it the main chamber. There's not really a name for it, so I just call it the main chamber. The middle section that is commonly called the velocity selection chamber, because really what it does is selects a velocity and allows it to go straight through. The rest of them get curved upwards or downwards. And then there's this first section over here that we haven't really looked at. The reason we haven't looked at it is because, well, The reason we haven't looked at it today is because really we've looked at it in a lot of detail in Unit 2. I call it the acceleration chamber. What's happening here? These mysterious cathode rays, well, they're not mysterious anymore, right? We know what they are. They're electrons. They're beams of electrons. These beams of electrons are accelerating from the cathode to the anode. They're speeding up. That's like a car doing what? Going down a hill. So in other words, we're going to say EI is equal to EF, and we're going to say QVI, potential, is equal to kinetic. So at the beginning of this section, it's potential. At the end of this section, it's kinetic energy, 1/2 mv squared. Then it enters the velocity selection chamber, where we filter out all but one velocity. And then it enters the main chamber, where we calculate the charge to mass ratio and see that it has a value that's so much bigger than any other value I've ever seen. Why don't we just use this speed right here instead of calculating the speed in the velocity selection chamber? Well, when we calculate that speed, that's not really necessarily the actual speed of the particles. That's the maximum speed, right? That's assuming the energy conversion for potential to kinetic is 100% efficient. If it's not, then they're not going to be going that fast, right? So unless we have to, we don't want to use this number for speed later on in the question, because we don't know for sure that the particles are going that fast. They could be, but we don't know that for sure. This is our little conclusion here, right? Thomson measured the charge to mass ratio of the electron, Q over m, really, really big compared to other charge to mass ratios that we already knew, which meant that the mass must be really small. Q over m is big. Well, the denominator, m, must be small. Q over m is bigger than anything else ever observed. Well, then m must be smaller than anything else ever observed. Therefore, it's got to be not just negatively charged particles, but subatomic particles. Let's take a look at a problem here. This is a beam of electrons. Already, okay, in 15.1, already we're acknowledging that it's a beam of electrons, okay? There might be problems where you're not told what it is, right? You have to find the charge to mass ratio or something like that and not assume that it's electrons, right? Thompson didn't know that they were electrons when he started. He did after he finished. Okay? We're looking at this as if we already know that these cathode rays are beams of electrons. Therefore, we already know the charge and the mass. I'm not going to write down the value of the charge and the mass of the electron because they're on my data sheet. I'm just going to write a little note, Q and M, to remind me that I have it if I need it. I can go back to my data sheet and find the numbers if I need it. Passes undeflected through a 0.50 Tesla magnetic field. That's going to be B, combined with a 50 kilonewton per coulomb, don't like that kilonewton, electric field. All perpendicular to each other. How fast are the electrons traveling? Here's what you gotta do in these problems. First of all, identify that you have a cathode ray tube. Okay, this is a cathode ray tube or something that's like a cathode ray tube. But then you got to identify which of the three sections of the cathode ray tube it really is. Because really, I've just taught you three types of problems, right? The acceleration chamber, the velocity selection chamber, and the main chamber. That's three separate problems, really. Which chamber of the cathode ray tube is this? It's the velocity selection chamber. Good. Tanner, how do you know that it's the velocity selection chamber? Two things, by the way, that I'm thinking of that kind of guide me towards that. Tanner, what's the one that guided you towards it? Okay. If we have an electric field and a magnetic field together, then that's going to be a velocity selection chamber, right? There's one other key word that leads me to that velocity selection chamber. Undeflected. Okay. I like the word undeflected because that's the only section where we would see that word undeflected, right? So let's use the velocity selection chamber. Let's derive the equation. Fm is equal to Fe. We're going to say QVB is equal to Q times E. Why don't I just write down the equation? Like the V is equal to E over B. I know that's what it's going to always turn out to be. Why do I derive it here? This doesn't appear on our data sheet. Okay? I don't want to try to memorize that equation. Okay, I want to look at this and say, okay, logically, Fm is going to be equal to Fe. I can figure out the equation easily if I remember that. Q's cancel. V does, in fact, equal E over B, as we expected. E is going to be 50 times 10 to the 3 newtons per coulomb. And we don't want those kilonewtons, right? Divided by B, which is 0.50 Tesla. 50 times 10 to the 3 divided by 50 times 10 to the minus 2 is going to give you 1 times 10 to the 5. Is that right? Sorry? I said 50 times 10 to the minus 2. And I just said 50 times 10 to the minus 2 because the division was easier, 50 by 50, right? Does that make sense, though? Okay, I could have just easily said 5 times 10 to the minus 1, right? Or left it there, but it was just easier division, that's all. So I think it becomes 1 times 10 to the 5 meters per second, which is, we know, a pretty typical speed for a charged particle, right? 10 to the 5, 10 to the 6 meters per second. Probably right here, because we got a speed that's in that normal range. Good. Okay. Not going to give you much time at all to work on these questions, but maybe enough time to solve for one of them before we do another example, okay? All right, if we're not having any trouble with that, I'm going to ask you to finish these up for homework tonight, for Monday. Take a look at one more example here, 15.2 on 758. This one says, when a beam of electrons accelerated to this speed, all right, that's good news, we're already given the speed, is directed perpendicular to a magnetic field, okay, that's going to be B, the magnetic field, but I don't like that micro Tesla thing. They travel on a circular path of radius 3.37 centimeters. Find the charge to mass ratio. Charge to mass ratio. All right, cathode ray tube, right? Which section of the cathode ray tube is this? The acceleration chamber, where the electrons speed up? Is it the velocity selection chamber, where they go undeflected and we can determine what the speed is? Or is this the main chamber where they go in that circle? Main chamber, right? What tells us it's the main chamber? Goes in a circle. That's one of it. Radius, yeah, it goes in a circle. Picture, sure, absolutely. A charge to mass ratio. We always find that in the main chamber. Lots of things that guide me towards that, right? Okay, again, we have an equation for the charge to mass ratio, but let's derive it again. mv squared over r equals qvb. Oops, b doesn't cancel. It's not b. What is it that cancels here? One of the v's, right? So it becomes mv over r equals q times b. B stays where it is. Sorry, q stays where it is. B's got to go down to the bottom. M's got to go down to the bottom. So I've got v over b times r equals q over m. Okay, let's figure that out now. V was, what was the value of V? 5.93 times 10 to the 5 meters per second. Divided by the magnetic field, which was 100 times 10 to the minus 6 Tesla. Times the radius, which was 0.0337. Okay, let's figure that out. Let's pull out the calculator to do that. If it'll turn on for me, there we go. Let's say 5.93 times 10 to the 5 divided by, use some brackets down here on the bottom, 100 times 10 to the minus 6 times 0.0337. Oh, you're 1.76 times 10 to the 11. I think that was the number that I'd given you, right? So I was right with it. Just wasn't positive. What would the units be for that? What is it? Yeah, absolutely. Charge to mass, coulombs per kilogram. Yeah, close. Coulombs per kilogram. Good? No, yes and no. The question, if you didn't hear it, was will that number ever change? Okay, yes and no. Yes, in the sense that if you're finding the charge to mass ratio for some other particle, obviously it's going to be different, right? Okay. If you're finding the charge to mass ratio for an electron, it should always be the same. Having said that, when you see a problem, sometimes they're purporting it to be based on experimental data, right? And when you're dealing with experimental data, all bets are off, right? You should get the value that we expect, but you don't always. So, on a test, I would say that if you get a number that's dramatically different than that, for the charge to mass ratio of the electron, you probably made a mistake. But if it's reasonably close, it's probably just the data that they gave you that made it a little bit different. Does that make sense? Yeah, no, that's exactly what it is. You calculate the speed of light. What if you get 3.02 times 10 to the 8 meters per second? Is it wrong for sure? Well, depends on the context of the question. If it's based on experimental data, then not necessarily. We know that it can't really be that fast, but experimental data can sometimes tell us it's that fast, right? Yeah, so it's kind of the same thing, yeah. All right. Homework for the weekend, guys. Homework for the weekend are the practice problems on page 756 and the practice problems on page 758. That's it.